Hello, good afternoon. I am Roberto Costas, and I'm going to give the talk named Rational Approximations, Hypergeometric Functions, and Difference Equations. This talk is presented in the seminar COMPUMATG in 2022 in Cuba. This is going to be online. And first of all, I would like to thank Professor Daniel Soria, and as well to the Agencia Estatal de Investigación of Spain, because it leads me to prepare these slides and be in this very nice conference. So the content of this talk are going to be split in three parts. So the first part is going to be about irrational numbers, where we present some principal preliminary results. We talk a little bit about irrationality measure. We present the Selberger algorithm, and we show all this information by using one example. This example is related with theta 3. Then we also gonna present some identities related with the Wronskians and the difference equations. And finally, we're gonna present some. We're going to show you some open problems. So I want to start with irrational numbers. So basically, we'll start with a real number, alpha, and this alpha number, we know that this is rational if it can be written like this, like a ratio of integers, where m is an integer, it's a general integer, and n can be a whole number, a positive integer. Of course, if it's not like this, then this number is called irrational. So irrational, like one clear example is the square of 2. I give you I let you to try that this number is in fact cannot be written like m over n, where m and n are integrals. This is a nice exercise if you want to try. At the same time, there are different kind of irrational numbers. For example, we have algebraic numbers. The algebraic numbers are those which are solutions of a polynomial with integral number coefficients. Transcendental numbers like pi, e, and some other numbers. And for example, we have this Euler-Mascheroni number, constant, gamma, and there are many others. But mostly people usually talk about algebraic irrational numbers and transcendental irrational numbers. So in fact, the cubic square of 7 is an algebraic number because in fact it's a solution of this polynomial. This is a simple exercise to try. Right. At the same time, it's impossible to find polynomial expressions so that these polynomials have a solution e or pi. So in order to prove some of the results about irrationality, we need to use, for example, this lemma. This is the irrationality lemma, which in fact tells you the following. So suppose that you have an x which is a real number, and suppose that we can find a sequence of integral numbers pn and qn, so that qnx minus pn is never equal to 0, and at the same time, when you take the limit when n goes to infinity, qnx minus pn is in fact equal to 0. Then we can state that x is irrational. Here we have a little sketch of the proof, and it's quite easy. So suppose that this number is a rational number, so x is p over q. Then you plug this p over q in x here and expand, so you have qn q minus pn p. Sorry, this is as it should be pqn minus qpn, but you know then this number is non-zero because this condition. So then in absolute value is greater or equal than 1 because this is an integral number. At the same time, if this is the case, then you can divide by the absolute value of q and in fact qnx minus pn is in fact greater or equal than 1 over absolute value of q, but this q is a fixed number, so this is not going to be never equal to 0 in the limit, right? So then this is impossible. So if these conditions hold, the number is irrational. All right, so observe that this lemma let you obtain not just one rational approximation, but maybe many rational approximations, right? So it depends how fast this rational numbers Pn, so these integral numbers Pn over Qn tend to x. So this is key of this problem. In fact, suppose that you have this x number, with the one we started with, and then we consider the set of real numbers R, so that which is constructed with positive numbers mu, so that this condition, so you have you need to obtain p and q integers, so that the x minus pq in absolute value is less than 1 over q to the mu. This mu is fixed, has a finite solutions, a finite set of solutions. So if this is the case, if you have a finite solutions of p over q, then mu is in your set. Okay, if you have infinite values, then mu is not in the set. So the rationality measure is defined like the infimum of these values, right? Of these values mu. So it is the case that can be computed. Okay. So in fact, observe that you also can define this in a different way. So suppose that you have the set of mu, so that x minus p over q less or equal than 1 over q mu has infinite values, infinite solutions. So then what you need to do is to obtain the supreme of this set, right? So in the previous case, you want to have only a finite set of solutions, but in this case we want to obtain infinite many p over q solutions. So then the supreme of these values is the irrationality measure. So for example, this is another exercise if you want to try. If x is rational, then the irrationality measure for this value is just 1. Now, Dirichlet proved in 1849 that if x is rational, then of course mu of x is greater or equal than 2. Okay? If you want to read something about that, you have some information in the web about how to see the proof of this result. Now, Ruth proved that in fact, if you have an algebraic irrational number, then mu of x is greater or equal than 2. So this for this result, Roth got the Fields Medal, and this is one of the very nice results of this about this problem. So one of the nice problems is, can we say, hold on, I think in this case there's a mistake. This is, if it's algebraic irrational, this is just equal to 2. Okay, sorry, I just copy and paste, and this should be equal to 2. So the problem, of course, is obtain some values for which irrational, so that the mu of x is strictly greater than 2. This is a nice problem to solve. Okay, so we have for one side the irrationality lemma, we have the irrationality measure that we want to obtain. So the problem here is to obtain rational approximation for these numbers, right? For this alpha we consider. By the way, some of these results about the rationality measures can be obtained by using continued fractions, and continued fractions are related with orthogonal polynomials, and in particular some of the cases you can find in the literature about these problems are connected with hypergeometric series. So one of the an hypergeometric series is in general like this. So you have a set of numbers A1 AR, B1 BS. So you have R is the number of A's that you have, and this is the number of B's. C is just any number. So then you need to obtain the infinite sum of this product of numbers. These are called the Pohammer numbers, or the shifted factorials, and you have here the definition for these values. Of course, k factorial is just 1 times 2 times k, right? So these kind of expressions are really useful for this kind of problem. So let me just show you a little detail. So suppose that you consider fn of c, if you want, like the hypergeometric series 2f1 on minus n b c c, right? This is called the Gauss function. Well, the Gauss function is more general, is a, b, c, c. So I'm going to consider this particular case. This is a polynomial, in fact, on c of degree n. And it's not difficult to see that, in fact, these numbers satisfy this recurrence relation. Okay, so this is useful because somehow, if you give me two of these values, let's say f0 and f1, I can compute f2 by setting here, for instance, n equal 1, right? N equal 1, you have f0, f1, so you can compute f2, and so forth. And in fact, in this particular case, it's simple to obtain f of 0, f0, which is just 1, and f1 is just 1 minus b over c z. Okay? So this is a nice problem to compute. Now, of course, it's not difficult by using this algorithm, the Seilberger's algorithm, to prove that if you give me any hypergeometric series, more or less in general, they satisfy a recurrence relation like this, right? So we usually would like to have this part equal to 0, right? Like in the previous case, right? So you can move everything to the left, and then you have to the right equal to 0. So we like to have like this here equal to 0, and you have in the left hand side some elements which depend on the hypergeometric series that you have. Okay, that looks a little ugly, but trust me, this is simple to reduce to a simple expression. Okay, so the key is you give me the hypergeometric series, and I would like to obtain for this hypergeometric series something like this. All right. And in fact, you can do. There is one algorithm by this guy. It is implemented in Mathematica and Maple, so you can just plug in your hypergeometric series, and it tells you the recurrence for such expression. So let me consider another case. I'm going to consider this Rn, like this infinite sum, which starts at n, and is 2k plus n plus 2 times minus k sub n, k plus n plus 2 sub n over k plus 1 to the 4th sub n plus 1. Right? So you have 4 terms down here, factorial. So you have 2 Pohammers up. So you expect to have this as a convergent series. And in fact, it's not difficult to prove that tends to 0. Okay, what is not easy, but it's a question of computing by hand, that this Rn can be written like an minus bn zeta 3. Zeta 3 is a zeta function at 3, and an and bn are going to be rational numbers. Okay, it's not really much difficult, but it's not trivial either. So a nice way to try is, for instance, you take R0, which is from k0 from 0 to infinity. So then you apply Seilberger algorithm, and in fact it tells you it's like this. So this Rn satisfies this recurrence relation. So if you give me R0 and you give me R1, and both are like this, then it's not difficult to prove that in general that this is the case. Okay, so you need to have Selberger for this expression, and then just some little calculations. Okay. In fact, look at this. What happens? So look at this. So this is a reconciliation. The initial conditions are simple, and at the same time, look at this. Because Rn is like this, it's not difficult to prove that An and Bn also fulfill this kind of recurrence. So for An and Bn, you have some initial conditions, which depends on the initial conditions of Rn. But this is possible to compute by using a computer and obtain this R0 and R1. Okay. But notice that you have this expression has polynomial coefficients on n of different degrees. You have polynomial degree 1, degree 3, 1 here, 2 here, 3, and then here 5. So I would like to have the same degree in all these polynomial coefficients. So what I'm going to do is I'm going to use like this expression. I'm going to redefine this like minus 1 to the n factorial. Sorry, there should be a square Rn, and if so, then this as Sn fulfill this reconciliation. You probably is like the previous line, is like the previous one, but now you have cubic, and here also degree 3. So now you have like a normalized degree 3 reconciliation with polynomial coefficients. This is much nicer, because then what I'm going to do is I'm going to divide by n cube all the expression, and then try to take some limit in order to obtain the behavior at infinity of Sn. This is one of the key of the problem. Okay, just a little detail. This of course is a reconciliation, and it's not difficult to transform any kind of reconciliation of, let's say, any order, but in this case like second order, like in one where you have really these difference operators. And for this particular case, as I said, if you divide by n cubic, you can compute the characteristic polynomial, which is like this: lambda squared plus 34 lambda plus 1. This 34 comes from this 2 times 17, right? And the roots of these polynomials, the characteristic roots are something really small and something which is also minus 12. It's minus 34. It's a big number and negative. So what we are going to do in the future is remove this minus, because we have this minus 1 to the n at the top. So now the problem is what to do with these two numbers, how these numbers are related with the problem. Well, I will show you in a moment. So let me just tell you that for this particular problem, it's not difficult to prove that Bn has this very nice expression. As you see, it's a finite sum of these binomial numbers, and of course An can be computed. It's just too large to write these slides, but you can find online in easily. All right, so the theorem we are going to use in order to obtain the behavior at infinity of An, Bn, and Rn, or as Sn, is the Poincaré theorem. So this result tells you the following. So you give me some different expressions like this, right? Difference equation of order d plus 1, and suppose that you have different modules of the roots. Then if Un solves this recurrence, then Un is equal to 0 for n large enough, or the ratio of in the limit of Un plus 1 over Un is sum of these roots. This is for some k as one of the roots of this polynomial. All right, so with that tells you that what is the behavior of Un at infinity. This is a very important result, because in the previous case we know that Rn, An, and Bn behave at infinity like this power or this power, but this power tends to 0, so I want to have Rn tends to 0, and I want to have An and Bn tends to infinity. This is something I would like to have. So in fact, if I go back and write Rn in terms of Sn, it's not difficult to see that Rn tends to 0. Yes, this is something that you can check numerically, and then An and Bn behaves like minus lambda 2 to the n, right? Because you have this minus 1 to the n that you need to apply somehow, right? Okay, but as I said in the beginning, An and Bn, they are not integers, they are rational numbers. So even though I have this, you can obtain this by taking this identity, right? I know that if this number tends to 0, then An over Bn approximates theta 3, right? So this is something I would like to obtain. So in order to do that, I'm going to show you another tool that I think is helpful to solve this problem. So the first thing is the difference equations. As you see previously, we just saw that in some situations, if you have hypergeometric series in your problem, these hypergeometric series, because the Seilberger algorithm fulfill a recurrence relation like this with polynomial coefficients. So where you have these polynomial coefficients, you have different degrees in general, but what happens is the jump of the difference of the degrees, it's increasing by constant rate. So this is very nice, or they have the same degree. So if they have the same degree, stop. This is the right way. This is the right one. If it's not, then you need to transform a little bit them in so that, as we did, every polynomial coefficient has the same degree. This can be done, I will say, in every case. Now, what happened, in fact, in the cases that you can find online about this particular, the zeta n, zeta 3, zeta 2, and some other values, is that the PD and P0 are connected. They are connected like this. So the PD of n, which is related with the u sub n plus d, is has the same polynomial as P0, but P0 have at n, and PD has at n plus 1, not at n plus d. You have at n plus 1. This is very nice. And n sub n is like the numerator, it's a polynomial of certain degree, and the n is like the denominator, so it has also a certain degree. And so we expect to have this polynomial has the same degree as this polynomial. So n and the n has the same degree. And it should be nice to have both equal to 1, right? If both are equal to 1, this is really cool. Okay. Now, let me show you a little bit about the Wronskians. So, the Wronskians appears in this problem in a very natural way. So, suppose that you have, as previously we have some rational number, some rational hypergeometric expression type, right? So that Rn is in fact can be written like as a sum of 4 sequences of numbers times 1, eta 1, eta 2, and eta 3, right? I want to have something like this. Then, what I want is to obtain a rational approximation of eta 3, and I want to cancel these two terms, what I need to do is to apply the Wronskians of R1 and 2. This Wronskian is defined like this. So you have Rn, A1n, A2n. You see, for this one you have R1, 2. R is the let's say the remainder, and then A sub 1 and A sub 2. So if you do like this, then R because this is a determinant, right? Oh, by the way, I said Rn, A1n, A2n, then you have Rn plus 1, plus 1, plus 1, then Rn plus 2, plus 2, plus 2, and then you have more terms, right, like 3 or 5 or whatever, then you have, this is a determinantal expression, so you have as many rows as columns. Then if you have, because if you have two columns equal each other, then the Bronsquian is equal to 0. Then if you replace R by this expression, then you have A0 here, which is A Bronsquian 0, 1, 2. Then you have A1, but then you have 1, 1, 2. This Bronsquian is equal to 0, so that cancels. Then you have A2, so you have 2, 1, 2. To have two columns equal each other is equal to 0, and then you have 3, so you have 3, 1, 2, eta 3, right? And because the determinant change of sign every time you switch rows or columns, because you switch twice here the 3, right? 3 with the 1 and then 3 with the 2, right? Then it remains the same sign. So in this particular case, the Bronsquian of this is just a linear combination of two terms where you have, let's say, the constant term and the term which is multiplied by the number you want to prove that this is irrational. Okay, so here is what you expect. So the Bronsquians of three numbers is just AI, AJ, and AK, right? With n plus 1, n plus 2. And this is standard, right? Okay, now suppose that now what we want is to obtain solutions, or which kind of equations fulfill this kind of Bronsquian, this Bronsquian. Okay, this is the one I want, or this, right? But in this particular case, I want this. How do I do it? So I know that A1, A2, A3, right? A1, A2, A3, even A0 fulfill the same, this is Seilberger difference equation. So what I'm going to do is I want to cancel P1. So what I do, I work with the first two equations. So then you multiply this by minus A2n plus 1, and then you multiply by this by A1, A sub 1, A plus 1, and then you subtract, and then lucky you have this time this minus this time this, which is the Bronsquians 1, 2. Okay, this is an exercise that you can try by yourself. Then the same with this. So you have A1n plus 2 times A2n plus 1 minus A2n plus 2 A1n plus 1. This is minus the Bronsquians n plus 1. Now you guess that this index means the first element of the first n that you need to consider in your Bronsquian. And then P3, in this case you have n plus 3 terms and n plus 1, then you need to have these determinants, right? This is not a Bronsquian, it's something more sophisticated, but it doesn't matter, because now what you want to eliminate is the P2, and when you do it, lucky you obtain some expression like this, right? You see the Bronsquians 1, 2, 3, and the Bronsquians n plus 1, 1, 2, 3. This is something very nice. So in fact, because you remove the P1 and P2, only survives P0 and P3. So this is the difference equation which that fulfills the Bronsquian that we need. Okay, so you see, probably this is a nice exercise that you can do. So in fact, if you have more terms here, you expect to obtain some kind of different equations for the Bronsquians that you consider. So this, in this particular case, you see is quite easy. Let's say, suppose that you only have two equations. You only have A1 and A2. You don't have any more elements. Then in this particular case, you only can do this once, right? You cancel this term, and then it still remains this factor. So how can we do so that we have we obtain a different equation for the Bronsons of 1, 2? Well, what you do is because you can write the first equation, or you can write both equations replacing n by n plus 1, right? So you have p0 n plus 1, a sub 1 n plus 1, and so forth, and the same thing here, right? So p sub 0 n plus 1, a sub 1 n plus 1 can be written like these three elements, right? So you can, if you multiply here by p0 n plus 1, right? p0 n plus 1, so you multiply everything by p0 n plus 1, then p0 a1 n plus 1 is a1 n plus 2 here, then a sub 1 n plus 3, so then they cancel each other, and then a sub 1 n plus 4. So then, surprisingly, you obtain this expression, right? I think it's a nice exercise for you to check what I said. So I multiply everything by p0 n plus 1, you see, it remains here with the first, it remains with the second, and then it remains here with p3, you see, you have p3 here both, and then a sub 1 n plus 2 is minus the Bronsken a sub n plus 1. Sorry, n plus 2, right? Because you have n plus 2, n plus 3. Right? And well, this is expression. Okay, so in the end, these Bronskens 1, 2 can be computed. All right. Now, as we said before, if all the polynomials they have the same degree, then pi has the leading coefficient like lambda sub I and t. So then these Bronskens we have can be simplified. Oh, you see, for one side, your coefficients a1 a2 fulfill this, and the Bronskens satisfying these difference equations, right? Are these difference equations connected? Well, I will show you that they are. So for the first, I know that the characteristic equation is lambda 0 plus lambda 1x plus lambda 2x squared plus lambda 3x cubed, right, equal to 0. So it has three roots, r1, r2, and r3. Now, for the second, it's not difficult to check that the Bronskens fulfill this. Okay, it takes you a little calculations, but it's not a tricky calculation. It's just you need to know what to do. So this is like lambda 0 squared. This is minus lambda 2 lambda 0. This is lambda 3 lambda 1. This is the lambda 3 squared. You multiply, divide, and finally you get something like this. So you see the roots are connected, and this is a very nice thing because you can compare the solutions of both kind of expressions, the solutions of the first difference equations, which are the coefficients of your related with your with your real numbers, and with the Bronskens, but related with these coefficients. Okay, so the problem, of course, is if you have this expression theta 3 of minus an over bn, if rn over bn fulfill like lambda over mu to the n, is this going to 0? Is this tending to 0? Well, this is the case only if lambda is less than mu in absolute value. But in fact, this is what happened in this particular case, right? Because remember, that was a really small number and that was a big number. The problem, of course, here is how to obtain the irrationality measure. This can be done, but we are not going to do in this particular case because it's a little tricky. But you can obtain, you can read some of the papers on theta 3 to see how to obtain these irrationality measures. Now let me finish this talk by talking about open problems. So I'm gonna just show you 3 different open problems. So the first one is to obtain better irrationality measures for different irrational numbers like pi. Right now I think pi is about 7,1 by Vadim Sudilin and Doron Selberger. And the same for theta 2. Well, theta 2 is just pi squared over 6. So this irrationality measure should be connected. And for some other numbers, right? This should be nice to know what happens. If is the better irrationality measure, can we obtain the best irrationality measure for these numbers? Well, I recommend you to go to the website by Vadim Sudilin, which is here if you want to try. And of course, another very nice problem is to prove that some numbers are irrational or not, like theta 5, theta 7, the Euler-Mascheroni number, the Catalan number. There are many other numbers for which we would like to know if they're irrational and if it's possible to obtain some irrationality measure for them. Well, we also know that they are irrational, like logarithm of 2, logarithm of 3. Well, there are many other numbers for which we know that they are irrational. And finally, another problem which also is very nice is, suppose that you only have something like this. Let's say in these conditions, right? With these conditions, we have something like this, and they are given, right? They are given. I would like to know which kind of numbers can be approximated by sequence of rational numbers fulfilling this kind of polynomial differences, right? Difference equations. This is a very nice problem to understand. For instance, for theta 3, we know that you have this expression. In fact, the one I'm showing you now is connected with theta 5. Well, sorry, theta 4, because suppose that you have theta 2 here, theta 3, and theta 4. This product should be connected with theta 4. And of course, there are many possibilities in this problem, with this problem. But you see, to know how to use Poincaré theorem, to know how to obtain the difference equations by using Selberger algorithm, and to do this irrationality lemma, there are really 3 things that we should know how to use in a nice way. Of course, I'm going to show you some further reading if you want to go in deep, but I really recommend you to go to this to the web of this guy. It's very nice. Okay, thank you for your time. I hope you enjoy and you understood most of the things. Here you have 3 references that you can check online, and if you need something else, just let me know.